Today's network lecture is going to cover transmission, the different types of broadcasts that are possible, and essentially the different pieces of the network that are involved in sending out information, sending out packets. So let's go ahead and look at the desktop. Okay, there's three types of casting. A cast is a transmission of packets, and there are three types that are common. A unicast is a cast with single network device. So essentially you've got a switch sending out information. Its ARP table lets it know what port that device that the packets are addressed to is on. And so the switch then sends those packets along that one single port to that one single device. Multicast, on the other hand, is a cast to a group of network devices. So maybe the switch is sending out information to several different hosts, and it does it through multiple ports, and that would be considered a multicast, sending out the same information to multiple ports. And then finally, broadcast is where the switch just floods all the ports with the packets that it's trying to send. This happens a lot when you are when you're building your ARP table in your switch. When you're first connecting devices to the switch, it will broadcast a request for ARP information, and then every host is expected to send back its MAC address so that the switch can build an ARP table and be able to route traffic then appropriately. In fact, one of the two reserved IP addresses in any range of IP addresses, if you'll remember, is the broadcast IP. And that, when the switch uses that IP, it sends out information to all of the devices in that segment or in that switch or in that subnet, whatever you want to call it. That particular IP address is reserved. Of course, you can't use it. It's just like the network ID. It is you have to subtract it from your range when you get the total number of usable addresses. So we're going to look at those three types. You've got a participation activity or two or three. Broadcasting collision domains. Broadcast domain is a logical network segment that includes all the devices that receive broadcast traffic. This is at layer 2. By default, all switch ports are in the same broadcast domain. That means if you have a switch, it's 24 ports. All of those 24 ports are in the same broadcast domain. And when the switch broadcasts packets, for example, an ARP request, then all of those ports get the same information. That is a broadcast. All router ports, on the other hand, are different broadcast domains. That is the fundamental difference between a switch, or one of the differences between a switch and a router, is that router ports are in different broadcast domains. You've got an incoming, and that's where your network traffic, or your internet, for example, your internet provider traffic comes in, and then you've got an internal side where all your local traffic moves around, and those two are different domains. A collision domain is where packets collisions occur in a network. A collision is a layer 2 problem where at least two frame transmissions collide and require retransmission. What happens is they bump together, now not physically because they're obviously not physical, but they cancel each other out and they're lost. And that packet or that frame, once it's lost, the data is lost. And so if you don't retransmit, then there'll be a hole in the message. The message will be missing some data. Each switch or bridge or router port is a separate collision domain. Each hub port is the same collision domain because hubs basically all operate at broadcast. They just flood the entire hub with all the data. Got another couple of participation activities. MTU, maximum transmission unit, is the largest protocol data unit. Frame size in a layer 3 transaction. That's the IP layer. A smaller MTU reduces network delay. Larger reduces overhead, so you can send fewer packets that are bigger, or you can send smaller packets that are smaller, or more packets that are smaller. MTU is specified in terms of bytes or octets and is based on the largest PDU that the layer can transmit. For an Ethernet, the frame is 1,500 bytes. So if you multiply 1,500 by 8, you get 125,000. That's how many bits, that's how many ones or zeros that an Ethernet frame can contain. Since the data and the physical layers usually add overhead to the network data layer, the MTU is a maximum frame size of a medium, minus the amount of overhead. So you have to subtract all the stuff for the data and the physical layers. The Ethernet maximum is 1518, and the MTU, basically the actual data amount is 1500 bits. Then you have 18 bytes, and you have 18 bytes of overhead. A jumbo frame is an Ethernet frame with a payload greater than that amount. These are associated with OSI model's data link layer. It's used on 1 gigabit local area networks and have a maximum frame size of 9,000 bytes. You have to have a lot of bandwidth to send jumbo frames because they're so big that you'll run into, like it says up here, you'll end up with a lot of bandwidth, a lot more traffic, or the packets are bigger, and so you'll end up with delay because it takes longer to send the bigger packets. Participation activities: carrier sense multiple access is a medium access control. That's a MAC protocol. We learned about those in the last module. Developed to decrease the network's collisions. A high collision amount decreases network performance because you have to consistently and continuously retransmit those packets. Remember, 2 packets that collide are lost, and now the message has a hole in it. CSMA prioritizes decreasing collisions since eliminating collisions is not possible. It just can't be done. You've got too many packets traveling too fast in opposite directions. There are some that are going to collide. It tries to detect the presence of a carrier signal from another node before attempting to transmit. So if that signal is sensed, then the device will wait. It'll wait until it doesn't sense that carrier signal anymore, and at that point, then it will transmit. So there are 2 types: carrier sense multiple access collision detection. That basically is a protocol used to prevent collisions by sending a jam signal when a collision is detected. And then collision avoidance, used to avoid collisions by using signal requests to send RTS and clear to send CTS before transmission. So basically what it does is it requests access before it sends, so that the other carriers are not sending information, so it cuts down on the collisions. More participation activities, and then a challenge activity, and at that point, then section 1 is over. All right, guys, once you've completed section 1, you can move on to section 2. If you have any questions, let me know either in class or via the Canvas inbox.